Renuka Devi is an assistant professor at the Department of Statistics, Presidency College, Chennai. Mrs. R. Renuka Devi has done her MPhil from Madras Christian College. She has 23 years of teaching experience and has published one research paper. She has also presented, participated, and organized conferences and workshops on statistics-related subjects.
Welcome to UGC lecture series on mathematical sciences. In last session, we discussed non-probability sampling techniques and ratio estimator, also the different characteristics of ratio estimator. We also did comparison of ratio estimates with mean per unit. In this session, I am going to discuss regression estimator, characteristics of regression estimator, comparison with mean per unit estimator and comparison with ratio estimator. We know that in ratio estimation it makes use of the auxiliary information. Like ratio estimation, regression estimation also makes use of the auxiliary information. Also in ratio estimation method, the regression is linear and the line passes through the origin. When the regression is linear and the line does not go through the origin, we have other methods which makes use of the linear regression. Now here we have the introduction. If the population mean or total estimated by fitting a linear regression when a study variate y is approximately a constant and a multiple of the auxiliary variate, then the estimator is called a regression estimator. We introduce now the difference estimator to increase the precision of the auxiliary based on the auxiliary information, the study variate y. Let y and x be correlated characteristics. If from simple random sample we obtain the unbiased estimators y bar and x bar of capital Y bar and capital X bar respectively, then the simple difference estimator is defined by yd bar is equal to y bar plus x bar minus small x bar, or a more general form of the difference estimator is given by yd bar is equal to y bar plus c into x bar minus x bar, where c and x bar are known quantities. The variance of the difference estimator is minimum when the value of c is given by c is equal to covariance of y bar and x bar divided by variance of x bar, which is actually the regression coefficient of y on x and it is denoted by beta. Beta is generally not known and it is estimated based on the values of the sample. Now we define the linear regression estimator as YL bar, where L stands for the linear regression is equal to y bar plus c into capital X bar minus small x bar, and c is given by beta, the regression coefficient, and it is estimated based on the sample values, which is given by beta cap is equal to b is equal to summation over I is equal to 1 to n yi minus y bar into xi minus x bar divided by summation xi minus x bar the whole squared, which is the regression coefficient of y on x. And now the regression estimator is YL bar is equal to y bar plus b into capital X bar minus small x bar, and the regression estimator for the population total is y cap, again L stands for linear regression, is given by n into YL bar, that is n into y bar plus b into x bar minus small x bar. When the regression is linear and the line passes through the origin and x bar is an unbiased estimator of the capital X bar, we get the linear regression estimator to be y bar. Now, the linear regression estimator y bar plus b into x bar minus x bar is a consistent estimator, that is for large values of small n, that is sample n tends to the population size capital N, x bar will become the population mean and hence this term becomes 0. We get the linear regression estimator to be the sample mean y bar. But regression estimator is not an unbiased estimator, it is a biased estimator, and the regression estimator is biased since beta is generally estimated by taking the ratio of the estimates of covariance of y bar comma x bar to that of variance of x bar, and the second reason is that it involves the product of two estimates beta comma x bar. And now we will get the expression for bias of regression estimator. In simple random sampling, the bias of the regression estimator YL bar is approximated by B of YL bar is approximately equal to covariance of x bar comma B, which will be negligible if the sample size is large. Now, we will derive this expression bias of the linear regression estimator. Now, we will obtain the bias of regression estimator in the following procedure. We know that YL bar is equal to y bar plus b into x bar minus small x bar. We assume that let small y bar is equal to capital Y bar into 1 plus E and small x bar is equal to capital X bar into 1 plus E1 and B is equal to beta into 1 plus E2. Also, expectation of E1 is equal to expectation of E2 is equal to expectation of E is equal to 0. We assume that expectation of E1 is equal to expectation of E2 is equal to expectation of E is equal to 0. Now, substituting the values of y bar, x bar and b in 1, we get YL bar is equal to, for y bar it is capital Y bar into 1 plus E plus, for b it is beta into 1 plus E2 into capital X bar minus, for small x bar it is capital X bar into 1 plus E1. Simplifying further, we get YL bar is equal to y bar plus y bar E plus beta plus beta E2 into x bar minus x bar minus x bar E1, and further we get YL bar is equal to y bar plus y bar E minus beta x bar E1 minus E1 E2 beta x bar, and taking y bar to the other side, we get YL bar minus y is equal to E y bar minus E1 beta x bar minus E1 E2 beta x bar. Taking expectation on both sides, we get expectation of YL bar minus y bar is equal to expectation of E y bar minus E1 beta x bar minus E1 E2 beta x bar. So, since we assume that expectation of E is equal to expectation of E1 is equal to 0, the first two vanishes, we get minus expectation of E1 E2 beta x bar. and we assume that x bar as x bar into 1 plus E1. From this we get E1 to be x bar minus capital X bar by x bar, and same way we get B to be beta into 1 plus E2. From this we get, from B is equal to beta into 1 plus E2, we get E2 to be B minus beta by beta. And substituting this in expectation of YL bar minus Y bar, we get minus beta x expectation of x bar minus capital X bar divided by x bar into B minus beta divided by capital beta, and on simplifying we get expectation of YL bar minus Y bar is equal to minus expectation of x bar minus capital X bar into B minus beta. So, this is actually minus covariance of x bar comma B. So, we know that regression estimator is not an biased estimator. So, it is not an unbiased estimator, it is a biased estimator, and expectation of YL bar minus Y bar gives us the bias of the linear regression estimator, which is equal to minus covariance of x bar comma B. Now, let us derive the variance of regression estimator. In simple random sampling, the large sample variance of the regression estimator is given by variance of YL bar is equal to variance of YL bar plus beta squared variance of x bar minus twice beta covariance of Y bar and x bar. Now, we will derive the expression for variance of regression estimator. So, it is variance of YL bar is equal to variance of Y bar plus beta square variance of x bar minus twice beta covariance of Y bar comma x bar, and substituting for each of these terms variance of Y bar, variance of x bar and covariance between Y bar and x bar, taking the common term outside, we get 1 minus f by n into s y square plus beta squared s x square minus twice beta s y x. We know that beta is equal to s x y by s x square, and beta squared would be s x y square by s x power 4, and we know that the correlation coefficient rho is equal to s x y divided by s y s x, and hence rho squared is equal to s x y square by s y squared s x squared, and we get rho squared s x squared to be s x y square by s y square, and substituting this in the term A, we get 1 minus f by n into s y squared into 1 minus rho squared. This shows that correlation coefficient is perfect linear and the value of rho to be 1, modulus of rho to be 1, then we get variance of the regression estimator to be 1 minus f by sy squared into 0. This term becomes 0, we get the variance of the regression estimator to be 0. Now, we will compare the regression estimator with mean per unit estimator. For a large sample size n, the variance of estimators of the population mean y bar is written as variance of y bar is equal to 1 minus f by n into sy squared. This is for mean per unit method, and variance of the regression estimator is 1 minus f by n into 1 minus rho squared sy squared. We can now here by comparing the variance of the mean per unit with variance of the regression estimator, we can see that the variance of the linear regression estimator is smaller than variance under mean per unit. We can observe that the variance of the regression estimator is always smaller where unless rho is equal to 0. So, in case rho is equal to 0 and both the estimator becomes the same, this correlation coefficient becomes 0, variance under mean per unit will be the same as the variance of the regression estimator. Now, we will compare the regression estimator with ratio estimator. We already derived that the variance of the ratio estimator as 1 minus f by n into sy squared minus 2 r rho sy sx plus r squared sx squared. Under regression method, the variance is given by 1 minus f by n into 1 minus rho squared sy square. Now, we will compare these two estimators. Variance of the regression estimator minus variance of the ratio estimator is equal to 1 minus f by n into 1 minus rho square sy squared minus sy squared plus 2 r rho sy sx minus r squared sx square. So, this is obtained from these two. We have variance of regression estimator, variance of ratio estimator, subtracting the one from the other, we get this term, and further on simplification we get 1 minus f by n. So, this is sy squared minus rho squared sy squared minus sy squared plus 2 rho r sy sx minus r squared sx squared. So, 1 minus f by n, taking minus 1 outside, we get rho sy minus r sx the whole square. 1 minus f by n into rho sy minus r sx the whole square. Now, here by expanding this in the form, it is in the form a minus b the whole squared, we will get the term in the previous line. Taking minus 1, we will get it is rho sy minus r sx the whole squared. Without loss of generality, we assume that it is equal to 1 minus f by n into rho sy minus r sx the whole squared, being a perfect square and it is greater than 0, and we have left hand side variance of yl bar minus variance of the estimator under regression ratio method to be greater than 0, and finally we get beta minus r the whole squared is greater than 0. So, here substituting for r and rho, we get finally beta minus r the whole square is greater than 0, which is always true unless beta is equal to r. If beta is equal to r, then the estimates by both the methods are equal. Now, we will have an illustration to explain the regression method and comparison of regression with ratio and mean per unit. We are given the capital N, that is population size to be 117, the sample size is 17, capital X is given and summation xi is given, summation yi small x bar small y bar also given. We have Sx squared, Sy squared and values of Sxy. We have to estimate the population total by the method of regression estimator, also compare its precision with the ratio estimate and mean per unit method. We will solve this problem. The linear regression method estimator as YL cap is equal to n YL bar and YL bar is equal to n into y bar plus b into x bar minus small x bar. These values are given in the problem. Summation xi is given, we can find x bar by dividing summation xi by small n, and summation yi is given, we can find small y bar by dividing summation xi by n, and beta it is given as summation xi minus x bar into yi minus y bar divided by summation xi minus x bar the whole square, which is nothing but syx by sx squared, and these values are also given in the problem. We get beta value as b is equal to syx by sx squared, b is equal to 0.5732 and r the correlation coefficient, which is by the formula Sxy by Sx Sy, and these values are given in the data, which is equal to 0.7235, and substituting the values in YL cap is equal to 117 into 1133.29 plus 6.5732 into 1230.49 minus 1140.06, and this estimator is estimated as 138660. Population total, linear regression estimator for population total, and the estimate of the variance is given by variance of YL bar is equal to, we know the formula is 1 minus f by n squared into sy squared into 1 minus r squared, and this is found out to be 94398.63 under regression estimator. Under ratio estimator, YR cap is obtained by substituting the values in the formula 1 minus f into n squared by small n into sy square plus r cap squared sx square minus 2r cap sxy, all these values are given, and r squared, r cap is estimated as r small r cap is equal to y bar divided by x bar, and this found to be 0.994. Variance under ratio estimator is found to be 149,235.01 and variance of under simple random sampling is found to be using the formula 1 minus f n squared sy squared by n. This is found to be 198,108.5 and relative precision of regression estimator to ratio estimator is variance of yr cap divided by variance of yl cap, and this is found to be 158.09 percentage, and relative precision of regression estimator to mean per unit method is variance of y cap divided by variance of the linear regression estimator, and it is found to be 209.86 percentage. So, based on the relative precision, we can conclude that regression estimator provides more precise estimates than the other two methods, namely simple mean per unit method and ratio method. And summary, today in this session we have discussed about regression estimator, bias and variance of regression estimator. We also compared regression estimator with mean per unit as well as ratio estimator, and we also did illustration based on the variance of ratio, regression and mean per unit method. The questions are: what is regression estimator? Obtain the bias of regression estimator. Define difference estimator. In simple random sampling, derive the variance of the regression estimator. Compare regression estimator with mean per unit estimator and compare regression estimator with ratio estimator. Thank you for watching UGC lecture series on mathematical sciences.